Hello friends, welcome back to my channel. In this video, I am going to solve another exercise question from book Topics in Algebra from chapter 4, Vector Spaces and Modulus. Question is, if V is finite dimensional and W is a subspace of V, prove that there is a subspace W1 of vector space V such that V is direct sum of W and W1. In our proof, for given subspace W of vector space V, we are going to construct a subspace W1 of vector space V such that V is direct sum of W and W1. So proof, here V over field F is a finite dimensional vector space and let dimension of vector space V is n. Also, let W is any subspace of V such that dimension of W is R with R strictly less than n. Now since W is a subspace of V with dimension R, W will have a basis say B1 consisting of R vectors V1, V2 up to so on Vr. Now since these are the basis vectors of subspace W, so these R vectors V1, V2 up to so on Vr are also linearly independent vectors in vector space V. Next, we have one theorem which states that if V over field F is a finite dimensional vector space and if u1, u2 up to so on um are linearly independent in vector space V, then we can find vectors plus 1, plus 2 up to so on plus k in V such that vectors u1, u2 up to so on plus 1, plus 2 up to so on plus k is a basis of vector space V. Note that m plus k will be dimension of vector space V. So, by this theorem, we can find vectors Vr plus 1, Vr plus 2 up to so on Vr plus k, where r plus k is equal to n. That is, we can find total n minus r vectors in vector space V such that set B consisting of these n vectors V1, V2 up to so on Vr, Vr plus 1 up to so on Vr plus k is a basis of vector space V. So, we have got this basis B of vector space V. Next, consider span of these n minus r vectors, that is span of Vr plus 1, Vr plus 2 up to so on Vr plus k will be a subspace of vector space V. Let U is any vector in vector space V. Now we can write this U in terms of this basis B as U is equal to A1 V1 plus A2 V2 plus and so on plus AR VR plus AR plus 1 VR plus 1 plus and so on plus AR plus K VR plus K. That is, we can write U as A1 V1 plus A2 V2 plus and so on plus AR VR plus AR plus 1 VR plus 1 plus and so on plus AR plus K VR plus K. That is, U is equal to U1 plus U2, where U1 is the vector A1 V1 plus A2 V2 plus and so on plus AR VR and U2 is the vector AR plus 1 VR plus 1 plus AR plus 2 VR plus 2 plus and so on plus AR plus K VR plus K. Now note that U1 will be a vector in subspace W, as U1 can be written as linear combination of V1, V2 up to so on VR, which are basis vectors of subspace W, and clearly U2 will belong to span of these n minus r vectors Vr plus 1, Vr plus 2 up to so on Vr plus k. Now since U is any arbitrary vector in vector space V, and we can write this U as sum of two vectors U1 and U2, where U1 is a vector from subspace W and U2 is the vector which is in subspace, that is span of these n minus r vectors. Therefore, V will be sum of the subspaces W and span of this n minus r vectors, that is span of Vr plus 1, Vr plus 2 up to so on Vr plus k. We will call this expression as 1. Next, let V is any arbitrary vector which is in intersection of subspace W and subspace span of Vr plus 1, Vr plus 2 up to so on Vr plus k. Now since V is in W, so we can write V as alpha 1 V1 plus alpha 2 V2 plus and so on plus alpha r Vr, and also we can write V as beta 1 Vr plus 1 beta 2 plus beta 2 Vr plus 2 plus and so on plus beta r plus k Vr plus k, since V is in span of these n minus r vectors. Now as these two expressions are of the same vectors v, so they are equal. Again, from here we can write, taking this whole linear combination to left side, we have this thing, alpha 1 v1 plus alpha 2 v2 plus and so on plus alpha r vr minus beta 1 vr plus 1 minus beta 2 vr plus 2 minus up to so on minus beta r plus k vr plus k is equal to 0 vector. Now note that these n vectors v1 v2 up to so on vr plus 1 vr plus 2 up to so on vr plus k are basis vectors of vector space V. So they are linearly independent and their linear combination is equal to 0. So we must have these n scalars, that is alpha 1, alpha 2 up to so on alpha r, beta 1, beta 2 up to so on beta r plus k, all n scalars must be equal to 0. Therefore, as these n scalars comes out to be 0 and we have expression of this type, therefore vector v must be equal to 0 vector. Now since v is any arbitrary vector which is in intersection of these two subspaces W and span of these n minus r vectors, therefore we must have intersection of W and span of v1 r plus 1 vr plus 2 up to so on vr plus k is equal to singleton 0. We will call this expression as 2. Therefore, from 1 and 2 we have V is the direct sum of subspaces W and span of Vr plus 1, Vr plus 2 up to so on Vr plus k. That is, V is direct sum of these two subspaces. That is, V is the direct sum of W and W1, where W1 is the subspace which is span of these n minus r vectors Vr plus 1, Vr plus 2 up to so on Vr plus k, which we have added to form a basis B of vector space V, and this gives the existence of such subspace W1 for given subspace W2 of vector space V, and this proves our result.